Good day, dear students. In the today lesson, we will see about the transformations like isomorphism of a transformation, also the invertible of a transformation, composition of a transformations. And also we'll see some problems regarding to these topic. So first of all, we comes towards the isomorphism of a linear transformation, which is actually a very nice property of a some transformations which are like one and onto. So here these are the two important definitions, and the definitions are in a similar way as a generalization of a one function and one onto function. So if we comes regarding the linear transformation, we say that if T is a transformation from V to W, which is linear from vector space V to the vector space W, then T is said to be one if T maps distinct vectors in V onto the distinct vectors in W. Mean for each element of a V, there is a distinct elements in V's distinct elements of a W. We have a distinct element in V such that it will perform the one correspondence. Like here you can see that one for each element of V. There is a unique element in W such that they are maps like in this way. And furthermore, we say that if T is a transformation from vector space V to the vector space W, a linear transformation is said to be onto when every vector in V there is at least one image in a pre-image in V such that T of a V is equal to W means it other in the other meanings like it's cover the whole range set of W, then it's said to be onto. And when you have note that it's a generalization of a onto function, we have many functions which are which and the others are onto, but there are these two definitions still separate. Like in some infinite sets, we have some transformations which are but not onto, or some are onto that are not one. Here one can see that it's cover the whole space. This is not one because the values are not covering the whole of that, but this mapping is onto because it's cover all the vector space W. And similarly, these are the other examples which are the onto W, like it covers every element of a set W. And sometimes if you find some elements in W which doesn't cover, then we call in that space that case that such a mapping is not onto. So here there is also the one good result regarding that. Mean if T is a linear transformation, then if T is then the kernel of T is equal to 0. Kernel of T means the collection of those elements whose image is equal to the 0. It means that if T is map, T is linear transformation, then its maps 0 only on 0. So this is the important property that it means only the 0 element we have in the vector space V such that T of 0 is equal to 0 and the range of 0 element is belongs to the W. So and furthermore, if T is and kernel of the following spaces are equivalent if T is a just a linear operator, then kernel of T is equal to 0 and T is onto. Onto mean it's cover the whole range set of T. Like V is equal to R of R T, a range of set is equal to the V. So this is the important result in this direction, but this is for the case of a linear operator. Otherwise, one and onto are not equivalent. If it's operator, then they are equivalent. Now, here there are examples like the contractions, like if we take T of V is equal to CV, this kind of operators. So they are always one and onto. And because, and look, this is the important examples of a shifting operator. Like if we take some elements from the R infinity, and if we define the operator in this way, then you can see that it's covered the elements from that one. And also this is another operator T2. One can see that this the second T2 is onto but not one. Like T2 is onto this sense mean each element of the range set there is a one element in the domain set that such that it's covered the whole space. And these are the two important examples which shows the relation that when the maps the examples of a onto which is not 1 1 and 1 1 which is not onto. So these are the two important of the examples. And if we go to further towards some another example, like T1 is a mapping from space of all polynomial of degree 3 to R4, and T2 is a mapping in this way, then one can see that if you put 0 on that, so the image is only the 0. Moreover, for that, if you put 0 on that, so it means this is the important example that the T map 0 only to the 0. It means the kernel set contains only the 0 element from the domain of that one. So here, furthermore, these are the examples of this transformation P and Q. If you put off that one, so T is a transformation from Pn to Pn plus 1, mean degree polynomial of degree n to the polynomial of degree n plus 1. So what the thing is that the operators are defined in this way. So one can see that these maps are the following maps are 1 1 and on 2. And here there are some other examples of the differentiable operator. Like if you take the derivative of x square, this is 2x, and derivative of x square plus 1 is also the 2x. It means this operator is giving the two answers on the same values. If we put x square or x square plus 1, the answer will be always the same. So it means this doesn't map 1 1. Like if you take the one element from here and one element from here, these two are the distinct, but their image is same in the range set. So we conclude that the differentiable operators are not always the 1 1. So here there is also another definition regarding that one. Mean if T is a mapping, T is a linear transformation from V to W, which are finite dimensional. If the dimension of W is less than dimension of V, then this operator T cannot be onto. And if the dimension of V is less than dimension of W, then this operator T cannot be onto. So 1 1 and onto, so these are the important relations. Like it means that if it will be 1 1, then it will be cover the whole elements of a whole space of a W. But if these they have this kind of two important relations, but then we can conclude the relation that the maps of transformations cannot be 1 1 and onto. For instance, if T have a mapping from R3 to R2, that it means that this type of operator either they are linear or nonlinear, but still these operator cannot be 1 1. Why? Because R2 dimension of R2 is 2 and dimension of R3 is 3. And similarly, this relation will also satisfy that mean these operator will not be onto. Now, if the linear transformation is 1 1 and onto, then we call such a transformation is a isomorphism. And isomorphism is a very important property of a and relation between the two vector spaces. Then in that case, if two vectors, there is a linear transformation between the two if two linear two subspaces or two vector spaces, then we call that both spaces are isomorphic to each other. And this have a also give us some important relations between that. Like every finite n-dimensional vector space is isomorphic to Rn. Like if you take any n-dimensional vector space, so this is then we can obtain a linear transformation which is 1 1 and onto. So this is the result in that direction. Furthermore, this is the natural isomorphism from Pn minus 1 to Rn. So the dimension of a Pn minus 1 is n, and the dimension of Rn is also n. It means we can find a linear transformation which is 1 1 and onto. Hence, we conclude that the both spaces are isomorphism. Both spaces are isomorphic to each other. There is also the natural isomorphism between M22 because the dimension of M2 cross 2 is 4 and the dimension of R4 is also the 4. Also the differentiable differentiation by matrix multiplication. So here, if we take the operator d from P3 to P2, like it's just take the derivatives of the given function, then we can see that this type of operators we get some relation that the dimension of P2 is less than dimension of P3 because the dimension of P2 is 3 and the dimension of P3 is 4. So it means that as the range set is less than domain set, so it means that such operator is not onto because of the relation we saw the condition before of that. So then if we comes about the composition and the inverse of a transformation, this is also the important, like composition is required for this is the same idea, like if T1 is the transformation from U to V and T2 is the transformation from V to W, then the transformation T2 or T1 is the is a transformation from in which we apply the T1 before and then the image set we apply T2. So it means that this is the transformation from U to W. So it means that we can get the direct relations with the help of that, which take the element from U and move it to the W. So this is called the composition of a transformation, and we can extend it like if we have the multiple transformations, then still we can obtain this kind of composition. But remember that the compositions are not always commutative. Like T2 or T1 is not always the same as T1 or T2. So here one can see that if T1 and T2s are linear transformation, that its composition is also the linear transformation. So proof is available here. You can go through from that, like it satisfies the both property of a linear transformations. Also the composition of a linear transformation, one can see that how we can make the composition. And this is the some useful examples regarding that. Mean if you have a T2 or T1, so first apply the T1 and on their image you need to apply the T2, and in this way we obtain its composition. Similarly, one can obtain the T1 or T2. In T1 or T2, first apply the T2 and then T1 because it will comes from right to the left side. So, and the important thing is that identity operator is always commutative, and one can see that T O I is same as T and IoT is same as T because identity operator doesn't behave like that. It's just remain the element as the same. And if we this is the further composition. So if we have inverse, then one can find the inverse of that in the case that whenever our operator is invertible, like you can find a linear transformation which is 1 1 and onto, then the inverse of that one is exist. Like inverse, if you have an element in a vector space V to W, then if T is a mapping from V to W, then T inverse is a mapping from W to the V. Like it's just take reverse of the elements of these metrics. Now one can see that how it's behaving, and it will be taking the idea of that one. So if T inverse is the inverse of T, then it always fulfills that relation that T inverse of TV is same as V, and T or T inverse of W is equal to the W. Mean T and T inverse are basically the inverse of each other. So for the inverse, one can see that how to calculate is one thing, and the inverse of the transformation exist or not. So that is the another thing. So like if we have a linear transformation, like T is a linear operator from R3 to R3, defined in this way, then determine whether T is 1 1 or not. And if T is 1 1, then find its inverse. So one can check the different criterias for that one. So we know that behind a linear transformation, there is a standard metric. So we just need to identify the standard metric first. And then from that standard metric, we need to find its inverse. If the inverse of that metric exists, it means that this linear transformation is 1 1, and its inverse we can obtain, just multiply with x1 and x2 and x3 with that vector, and we obtain its inverse. So this is the very important example, and this type of example is also available in the assignment number 10. Like if you have a linear operator, just obtain the standard matrix from that, from of its form, by the form of its coefficients, and just take the elements in the first row, second row, third row of that one, and then this is the t. So if you find and check that if the metric t is invertible, like inverse of t exists, then it means this transformation is 1 1, and one can find its inverse. And from that inverse, this inverse is actually the standard matrix of t inverse. So if you multiply this with the vector x1, x2, x3, so we will obtain the t inverse. And then one can check that T O T inverse is equal to identity, and T inverse OT is also equal to identity. O mean its composition. So one can see that these relations are always hold. And moreover, if both T1 and T2s are the 1 1 linear transformation, then T2 OT1 is also a 1 1. And T2 OT inverse is same as T1 inverse OT2 inverse. So it means that if we have a composition, then their inverse we can also obtain the relation in the opposite form of that. So this is the idea will be same as the matrix, the inverse of a metric. Like you remember that, just recall that AB whole inverse is equal to B inverse A inverse. So here the composition is working in the same manner of that case. So similarly, if you have a more mapping, so the T2, it's a like T3 or T2 or T1 whole inverse is equal to T1 inverse or T2 inverse or T3 inverse. So this is actually relation between that one. And one thing more about this topic is actually the metrics of a general linear transformation. So we know that behind the linear transformation, we can always obtain the standard metric. So here, one can see that if we have some particular basis, then we can add that basis and obtain the elements from that. For instance, if u1, u2, and up to un, these are the bases of Rn, then if we multiply with the metric A, we can obtain the distinct elements of that one. And with the combination of that, we can see that these are the bases of a TU1, TU2 up to TUN. And if we combine that, we can also obtain the standard matrix of a linear operator T. So this is basically the idea of these matrix of a linear general transformation, like we can combine of these ones. And this is also the one nice example regarding that. If T is a linear transformation from P1 space of all polynomial of degree 1 to space of all polynomial of degree 2, then T of Px is equal to, like define this mapping is a T of Px equal to x times Px. Then find the standard matrix of T with respect to the standard basis of a B and B star. So what we need to do is that just put the values of a u1 u2, because these are the bases, and if we plug the values of that one in our operator, in the linear transformation T, then we can obtain the values like T of u1 equal to x and T of u2 is equal to x square. These are just the output of that mapping. So one can see that since this is the in a P2 contains the all elements of a polynomial of degree 2 whose dimension is 3. So if we pick the coefficient, so it will be the 0 coefficient of a constant, coefficient of x, and coefficient of x square. So the coefficient of x is 1, and the coefficient of x square and the coefficient of constant is 0 over that. So it means it's only will become 0, 1, 0. And here for TU2, one can see that the coefficient of his x is equal to the coefficient of x is 0, coefficient of constant is 0, and coefficient of x square is 1. So it means it will become 0, 0, 1. Now, if we combine these twos, then we can obtain the matrix with respect to B and B star. Like if we combine that, so this is the standard matrix of this. So similarly, we one can obtain the some other examples regarding that one. So for instance, this is the example like T is a linear transformation obtained in that one where there is a standard matrix available for a linear transformation. Now find the matrix of a for a transformation T with respect to the basis B, U1 and U2 and B star like which is the basis set of R3, V1, V2 and V3 where U1, U2s are available as well as V1, V2, V3s are available. Now, if we find the matrix transformation T with respect to the basis B, what we need to do is that just plug the entry of a basis in the map T. Like if we put 3 and 1 over here, we can get its images. And similarly, if we put 5 and 2, then we will get the 2, 1 and minus 3. Now, from these images, one can see that one can express this as a linear combination of a V1, V2 and V3 because V1, V2, V3 is a vector space. So if we combine only U1 and U2, then it means we obtain the matrix transformation with respect to the B. And if we obtain like it's a linear combination with V1, V2 and V3, then we can obtain these entries like which are 0, 1, 0, minus 2 and 3, 1 and minus 1. And if we combine these entries, we will obtain a matrix, which is a transformation from B star to the B. So this is basically the idea to obtain these expressions. And similarly, so if there are some other results regarding that, one can obtain like if T is a linear transformation from P2 to P2, which is the operator, and defined in this way. Then find the matrix T relative to the basis of that one. So what we need to be do is that we just employ the values of this into the mapping T, which is defined over here. Remember that one mean P1. If you put 1, so it will becomes like since this is the P2 transformation. So if you put 1 over here, then it will only obtain the constant as a 1. Similarly, Tx square, the images of that one. Now with the images of that one, we need to be compare the coefficients of a constant x and x square, then we obtain these values. And when we combine these, we can obtain the standard matrix of T. So this is basically the idea and similarly use the direct procedure to compute this. So whenever the mapping is available, which is from P2 to the P2, so we can also add some value over there and can get its output. So for instance, and also by the mapping, one can see that check the part B to computing of these values directly. So here, if we have the metric available, so we can employ the value of a one, just put their coefficients on that and multiply, so we can get its output. And furthermore, if we plug these values into the given linear transformation, then we can also obtain the values. And in that case, we will see that the answer of both output will always be remain same. So this is basically the idea of that one. Now, if we comes towards some problems regarding the examples, like if T is a linear operator from R3 to R3, then determine whether T is invertible or not, like inverse of T exists and not. If T inverse exists, then find the inverse. So remember that behind the linear transformation, there is a standard metric A. So what we need to do is that for that metric, just one can compute its determinant or check that is this metric invertible or not. If the inverse of that metric exists or determinant is non-zero, then it means this metric is invertible. And the second thing is that if it's invertible, then find its inverse. So just compute the A inverse and multiply with A inverse with X, Y, and Z. Then we obtain the T inverse of X, Y, Z. So this is the idea, like just compute the A inverse and multiply with X, Y, Z. If A inverse exists, it means the T inverse exists. And if A inverse does not exist, it means the inverse of T does not exist. In the problem number two, like T is a linear operator, linear transformation from P1 to R2. one can see that the dimension of both are same. So it means one can see that this T is isomorphic. And T is defined that T of Px equal to like P0 and P1. So P1 mean the polynomial of like if you have a polynomial of degree 1, so put 1 on that. So find the value of T 1x. So if you put 1x, so 1x is a polynomial of degree 1. So it means it will give you the same answer like if as you put the p0. P0 means just put the value of x equal to 0 in a plus bx. And moreover in p of 1 is mean that just put x equal to 1. So if you put the value 1 minus x, you will get some answer in R square. Similarly, show that this operator is a linear transformation, mean it fulfills the both conditions that T of P x plus qx is same as T of px plus T of qx. For all px qx is coming from the P1. Moreover, T of alpha times px is same as alpha times tpx. So it will be fulfill both conditions, and this will shows that such a uh, transformation is a linear transformation. Moreover, one can check that is this T is 1 1 or not. So there are many criteria. One is that like that if T if is 1 1, then the kernel of a T is equal to 0. It means T maps 0 only to the 0. So one can apply this and obtain the results of that one. Now in the next, if T is a linear operator from R3 to R3 defined in this way, then find the matrix T with respect to the basis this where V1, V2, V3s are available. We know that if we apply T of V1, we can obtain one vector. T of V2, we can obtain second vector, and T of V3, we obtain third vector. If we just write these vector in a column form and combine them, then we obtain the matrix for T with respect to the B, obtaining the basis V1, V2, and V3. And in the problem number next 40, if T is a find the composition T3, T2, or T1, where T T1, T2, and T3s are available in this way. We know that if we apply T3, T2, or T1, then first of all we need to operate T1, then its answer need to apply the T2, and then its answer need to apply the T3. So this is the idea that like find the composition of a three transformations. Now, if you have any question from the topic, you can ask your question.
Uh, Sir, can you repeat problem 39? Can you explain it again?
Yes. In problem number 39, V1, V2, V3s are available, which are the basis for a mapping T, and T is also available. Now, if you put T in V1, like suppose like if you put 1 minus 1 and 0, you will definitely get some answer. Am I right? Like if you put suppose if I am putting here the T of a 100, I will get the answer 2 2 and 2. Now I hope you understand. If I put 100, it will give 222. So if you write the 222 in a column form, then it will becomes the first column of a matrix T. Now again, if you put the second entry on that, you will get some vector, and that will become the second column of T. And if you put V3 in this transformation, then you will get another column, which is the third column of a matrix. So if you combine that to P1, P2, P3, it will gives you the standard matrix of a this operator T. Let me give you the example. For instance, like if you have some operator, for instance, if t is a operator, say like x, y is defined in this way, say 4x minus y, and say here uh, minus x plus 5. This is t is a linear operator, and suppose the basis set we have is say in the basis set, suppose we have some entries like 1, 2, and the second is we have say minus 1 comma minus 3. So this is also the basis of a R2, which is this is the basis, because determinant if you make a matrix, then determinant is non-zero. Now, if you apply the T of a 1, 2, then one can obtain, if you put 1, 2, 1, what we obtain from that in this transformation, if we put 1, 2, then it will becomes 4 minus 2, which is equal to 2. And if again we put 1, 2 over here, then it will be like here, suppose we have some 5 times y, suppose like this is the linear transformation. Now if we put 1, 2 again over here, then it will be 10 minus 1, which is 9. So this is the first entry, and if you apply the t again on the second, like minus 1 and minus 3, then if we plug this value in the mapping, then one can see that it will be the minus 4 plus 3, which is minus 1. Again, if we put this value over here, then it will be the plus 1 minus 15. That gives us minus 14. Now, if we compute the matrix, if we find the matrix is like just need to be combine of that and obtain the 2 cross 2 metric for this one. For instance, like the metric for this is a 2 cross 2 metric, like it will obtain the entries in that form, like 2, 9, and minus 1 minus 14. So this is the matrix of a for the matrix for the basis set of that. And as you recall that this result is the examples are also available over here. For instance, like like you have a u1 and u2. Whenever you employ this value over here, when then its combination will gives us a standard metric for that. For instance, here, yes. So if you plug the values of that and with the coefficient, if you put the coefficients of that one, we will get the values over here. And when we combine these three, it will gives us a metric T. Sometimes we call this matrix as a TB, and here you can see the matrix is also called the T metric in this form, and in the basis you can just write a B, because the B is a basis set. So this is basically the idea for a computation of a uh, the matrix for T with respect to the basis set B of R3. Any other question? Yes, students, just you when go to from that topic, hopefully the concept will be more clear to you. Like all these things are included in the topic. So just I advise you that please go through from the topic and work with the examples. As much as you will go through with the example, one can interchange the example and see the results. And when you will comes up to the exercise problem, you will really see that and you can appreciate this work. So the things are available over here. If you have any question, you can ask. So is there any further question from your side? Okay, if there is no question, then we can stop the session over here, and I will upload the lesson and also the topic on the my module website of MAT2611. Okay, have a good day and goodbye.